Hello and welcome back to Pyman Tutoring. This is part 2 of the limits of functions. Now in the previous video we talked about the limits of functions as x approached a certain value, a 0 or a 2 or a 5, some numerical value. In this second part of limits we're going to look at the values of functions as x approaches infinity. Let's begin. Let's begin with a quick reminder about function notation. We often write down an equation, let's say y is equal to 3x plus 4. What we have here is a y coordinate, which is a function of the x coordinate. So we can equally write this as some function of x. And these terms y and f of x can be used interchangeably. And as we move more in towards calculus, we'll be employing more of the function notation rather than the y notation. And this allows us to do things like, what is the function of 2, which simply means place the value of x equals 2 into this equation and you get 3 times 2 is 6 plus 4 gives me 10. And you can think of the function f as a blank box. He said drawing a white box. We're feeding in a value of x, and out the other side is coming the value f of x. In this case, we're feeding in a value of 2. The function inside is completing the operation 3x plus 4, and what's coming out the other side is the value of 10. So just because we're going to be interchangeably using f of x and y, just wanted to make sure everyone was comfortable with function notation. Now, if we have a simple function, simple linear function, let's say y equals 2x in this case. So y, oops, where's my cursor gone? There we go. Y, which is a function of x, and that function of x is just 2x. And now we want the limit as x tends to infinity of f of x. So what happens as x tends to infinity? Well, we can see on the graph that as x is growing in this direction, y or f of x is growing uncontrollably in the other direction, and so the limit as x tends to infinity is infinity. Similarly, if we have a quadratic situation, y equals, let's say, x squared plus 2x plus 3. The graph in this case, we know when x is 0, y is 3, or f of x is 3. It's a parabola with a positive coefficient, so it's opening up in this kind of fashion. And again, we can see that the limit, the limit as x tends to infinity of this new function of x is again going to be infinite. X is growing in this direction, y is climbing all the way up and heading towards infinity. Now let's take a look at rational expressions, and you'll probably remember these from your previous year. We had things like the limit as x tends to infinity of some polynomial, let's say 6x squared minus 2x minus 1, all divided by another polynomial, 5x squared minus x plus 1. And this is when we were dealing with the question of asymptotes and plotting such rational functions by determining things like the asymptotic behavior. And what we did in those cases was we said, well, we're going to divide each of those terms by the highest power of x available to us. So in this case, we have x squared. So we divide the first term on top by x squared, and we're left with just 6. We divide the second term by x squared. 2x divided by x squared leaves me with 2 divided by x. And the last term would be 1 over x squared. Now, if we divide everything on top of a fraction by something, we must do the same on the bottom. And so on the bottom, we get 5x squared divided by x squared is 5, minus x divided by x squared gives me 1 over x, and plus 1 divided by x squared. And now it's a simple case of allowing each of these x values in the denominators to grow to infinity. And what happens as 2 over x tends to infinity is that the value of that function will tend towards 0. So basically this term will tend to 0, this term will tend to 0, as will this and this. And so as x tends to infinity, this rational function will tend towards 6 over 5, which is just the ratio of the leading coefficients in this rational function. And this is always the case when the degree of the numerator matches the degree of the denominator. And so what we have graphically is that we have a function that has an asymptote at y, or f of x, equals 6 over 5. So this function will tend towards this value as x tends towards infinity. And, it might come this way or it might come this way. We need to do some more work to determine which of those it is. Similarly, we learned that if you have a rational expression and you want to know the limit as x tends to infinity, but you have the case of a lower degree polynomial in the numerator compared with the denominator. So in this case, we have 4x cubed minus 1. We can do the same as before. We can take the highest power of x available to us, and we can divide by that power. So we get x squared over x cubed gives us 1 over x. X over x cubed will give us 1 over x squared. 2 over x cubed will give us 2 over x cubed. And on the bottom, we're left with 4x cubed divided by x cubed minus 1 divided by x cubed. And I think you can see that as x tends to infinity, everything on top here will tend towards 0, and the denominator will tend towards 4. And so in this case, our function is tending towards 0. And again, this is always the case when you have a lower degree numerator compared with the degree of the denominator, the horizontal asymptote will be 0. As x tends to infinity, y or f of x will tend towards 0. And I'm sure you remember the third case, which is that if we want the limit as x tends to infinity of a rational function where the numerator is actually of higher degree than the denominator, then this we could apply the same technique, but that would not work. If we divided top and bottom by x cubed, we would find that on the bottom we have x squared over x cubed plus 1 over x cubed. Both of those would tend towards 0, so we would end up with 2x on top and 0 on the bottom. So that does not give us a clear indication of the limit of this function. In these cases, when the numerator is a higher degree than the denominator, we need to do the division and break this function into two pieces. So before we go any further, let's do that, and hopefully you remember how to do long division of polynomials. So we're trying to divide x squared plus 1 into 2x cubed, and it's a good idea to put all the terms, no x squareds, no x's, and nothing for a constant term. And then we can start dividing in. Well, x squared going into x cubed, we know that we need x, at least x of those. We've got 2x cubed, so the x squared will go in 2x times. And then let's see what we're left with. 2x times x squared gives me 2x cubed. And the 2x times 1 gives me no x squareds, but it does give me 2x's. And if I subtract those, I'm just left with 0x minus 2x is minus 2x. And so that's my remainder. So we can now say that 2x cubed divided by x squared plus 1 is equal to 2x minus 2x, which then the 2x still needs to be divided by the x squared plus 1. We left it there as a remainder, but really what's actually left is negative 2x still to be divided by x squared plus 1. And this allows us to now see more clearly what happens as x tends towards infinity. So in this second term, we now have a higher degree on the bottom than on the top. And we know that when the degree on the denominator is higher than the numerator, that this is going to behave like the second case. And so this will tend towards 0. And so as x tends to infinity, this function is going to get closer and closer to the line y equals 2x. So we have the case of an oblique asymptote. So if we imagine the graph of y equals 2x, this will be our asymptote. And then this function when x is 0, y is 0. And we can see from the function that when x is positive and large, the function is positive and large. So we know we are approaching this asymptote on this side, and when x is negative and large, the numerator becomes negative and large. The denominator stays positive. So that means we're getting large and negative. Now when x equals 1, we have 2 divided by 2, which is 1. So 1, 1 is on this graph. And when x is negative 1, we have negative 2 divided by 2, so we have negative 1. And so this graph actually looks something like this. And as x tends to infinity, the function tends to infinity. So let's just do some examples to solidify those ideas. Let's suppose we're asked for the limit as x tends to infinity of 5 divided by x all over 6 divided by x minus 1 over x squared. Now if we substitute in x equals infinity, we get 0 over 0. So that doesn't work, but let's try multiplying top and bottom by x squared to give us something more familiar. X tends to infinity, we'll get 5x on top, we'll get 6x on the bottom, minus 1. And this now looks much more familiar. We've got the same degree of polynomial on top and bottom, and so we know that as x tends to infinity, this function will tend towards the ratio of those coefficients. Let's look at another. The limit as x tends to infinity of 3 divided by x cubed minus 2 over x squared divided by 1 over x. Now what should we do here? The denominator is a problem because when we feed in infinity, we're going to get 1 divided by infinity, which will give us 0 in the denominator. So let's begin by multiplying top and bottom by x. So we have the limit as x tends to infinity of 3 over x squared now, minus 2 over x, all divided by 1. And now as x tends to infinity, the top tends to 0 and the bottom tends to 1. So we're left with the limit being 0. Now in the previous video, we used some properties of limits without really talking about them. So let's just take a more formal look at properties of limits. It's often useful to break a function into pieces and evaluate the limits of those pieces separately. The first rule says that the limit as x tends to a of a sum or difference of two functions can simply be evaluated by finding the limit as x tends to a of the first function and then adding or subtracting, depending on what you're doing in the first expression, to the limit as x tends to a of the second function. So that often makes life nice and easy. Break the function that you're given into two manageable pieces and then evaluate the limits of those two functions separately and apply the appropriate addition or subtraction to the limits. Similarly and intuitively, I guess, the limit as x tends to a of some constant multiplied by a function. If you have that situation, you can simply pull the constant outside the expression and evaluate the limit of the function on its own, and then multiply by the constant after the fact. So that's useful. The third type would be the product version of rule number 1. So that says that if you want the limit as x tends to a of the product of two functions, then it's perfectly okay to evaluate that as the limit as x tends to a of the first function, and then multiply the result by the limit as x tends to a of the second function. So those are all very intuitive, I think, and the last case, to be just a little bit careful with this one. If you have the limit as x tends to a of f of x divided by g of x, you can simply divide the result of the first limit by the result for the second function limit. But that's only true, of course, if the limit as x tends to a of g of x does not equal 0. Otherwise, this division blows up to infinity. There's one final version, and it really falls out from the product rule, but we'll state it explicitly here. The limit as x tends to a of some function of x raised to the power of n, just means f of x multiplied by itself n times. So we know by the product rule that this will be the limit as x tends to a of f of x, all raised to the power of n. So we can pull the exponent outside the expression. The next example we need to look at is for trig functions. We previously looked at the limit as x tends to 0 of sine x over x, and we said that that was equal to 1. Now we're looking at the limit as x tends to infinity of sine x over x. And we're going to state without proof that that is equal to 0. Now we need a little bit more mathematics to be able to prove those two. So for now, we'll just take those as given, and then we can use them in a similar fashion as we saw in the last video. So for example, if you are asked for the limit as x tends to infinity of sine 2x divided by x. And we simply have to make this expression look a bit more like the expression that we're given. So we can do that by manipulating the denominator. So that's the same as the limit as x tends to infinity of sine 2x over 2x, which is the format we're looking for. And then to balance this 2 we've put on the bottom, we're going to put a 2 on top. And we know from our limit rules that we can pull that 2 outside. So that's 2 times the limit as x tends to infinity of sine 2x over 2x. And now remember that these 2's in this expression don't actually affect the value of this limit. We can show that, if you like, by putting u is equal to 2x, doing a substitution. And then we know that as x tends to infinity, u is also tending to infinity. And so sine 2x over 2x is the same as sine u over u. We're looking at the limit as x tends to infinity, and that's the same as the limit as u tends to infinity. So this expression is exactly the same as this expression, and so we know the limit of this second term over here is going to be 0. 2 times 0 is equal to 0, and therefore the limit as x tends to infinity of sine 2x over x is 2 times 0, which is 0. One more quick example using that particular limit. So remember, we're using the limit as x tends to infinity of sine x over x is equal to 0. That's the unproven statement that we're using in these examples. And we are asked in this particular question for the limit as x tends to infinity of sine of x squared divided by x. Now we can apply the same trick as last time to try and make the denominator match the sine piece here. And we need another x on the bottom. So we better put an x on the top. So we can say that this is the limit as x tends to infinity of x times sine of x squared over x squared. Now we have a product of two functions, so we apply our limit rules that says we can break that into the two limits. So we've got the limit as x tends to infinity of x multiplied by the limit as x tends to infinity of sine of x squared divided by x squared. And this piece produces a 0, and this piece produces infinity. Multiply by 0, you get 0. And if you actually plot that function in Desmos, you can indeed see that the sinusoidal oscillations are collapsing down towards 0 as x tends to infinity. To finish off this video, let's just do a few more examples to keep you fresh in terms of evaluating limits. So limit as x tends to 1 of x squared plus x. Remember, our first port of call is always to plug in the value and see what we get. Plug in a 1, we get a value of 2, and that's the correct answer. That's the limit of that function as x tends to 1. So no more work to do there. 2, the limit as x tends to 1 of 4x squared minus 1 over 4x squared minus 4x plus 1. First thing to do is plug in the values, and we get 3 on top. We get 1 on the bottom. The answer is 3. The limit as x tends to 1/2 of 4x squared minus 1 over 4x squared minus 4x plus 1. So the same expression as above, but now with x equal to 1/2. And when we do the substitution here, we'll end up with our old friend 0 over 0, which is no good to us. So step 2 is, can we factorize? And indeed we can. So we're left with the limit as x tends to 1/2 of, factorize this, we get 2x minus 1, 2x plus 1, because that top expression is a difference of squares. And the bottom expression factorizes to 2x minus 1 into 2x minus 1. So we can see that we've got a common term top and bottom, so there's a hole in this function at x cannot be equal to 1/2. And so we're left with the limit as x tends to 1/2 of 2x plus 1 over 2x minus 1. And now if we plug in the values, 2x plus 1 will be 1 plus 1, that's 2. 2x minus 1 divided by 0. There's no more factoring to do. There's nothing else we can do to simplify this expression. And so this limit does not exist. And that's always a possibility too. And I think you can see that if we plug that function into Desmos, that at x equals 1/2, there is actually an asymptote. And so the function is approaching positive infinity when you come from the positive direction, and negative infinity coming from the negative direction. So very clearly the limit at x equals 1/2, or as x tends to 1/2, does not exist. A couple more quick examples just to cover every eventuality. Let's suppose we were asked for the limit as x tends to 0 of 5 plus x to the 4th minus 5 to the 4th divided by x. And clearly if we simply try to evaluate by feeding in x equals 0, we get our old friend 0 divided by 0. So what to do next? Well, whenever you see a negative sign between two things that have positive powers, you know you've got a good chance of using a difference of squares. Even though in this case we're seeing a power of 4, power of 4 is simply a power of 2 squared. So we can rewrite this expression 5 plus x to the 4 minus 5 to the 4 is the same as 5 plus x squared minus 5 squared squared. And so we have a squared minus b squared. And we know that we can write a squared minus b squared as a minus b. Well, a in this case is actually 5 plus x squared, and b is 5 squared. And we have to multiply that by the conjugate of that expression, 5 plus x squared plus 5 squared. And we've got all of that divided by x. So we have the limit as x tends to 0. Now, this thing here is again a difference of squares. So we can break it up one more time. We can break it into 5 plus x plus 5 multiplied by 5 plus x minus 5. All of that is multiplied by this second bracket. Well, let's expect, there's nothing we can do here. This is not a difference of squares, it's a sum of squares. So let's just multiply this out. Using FOIL on the first bracket, 5 times 5 is 25. We get 5x's and another 5x's, so that's 10x. And we get the x squared term. And then we've got plus 5 squared on the end is 25. And remember from the original expression, all of this is divided by x. So that looks messy, but it will clean up nicely. So let's simplify this first bracket. We've got 10 plus x in here. 10 plus x. And in the second bracket, we've got 5 plus x minus 5, which just leaves us with plain old x. And in the third bracket, 25 plus 25, we've got a 50 term, we've got an x squared term, and we've got a 10x term. All divided by x. Now we've got a common factor of x, top and bottom. So we know we can cancel those out as long as x is not equal to 0. And we're left with a limit as x tends to 0 of 10 plus x into x squared plus 10x plus 50. And now if we substitute in the value of 0, we will get 10 multiplied by 50 is 500. So a bit of factoring, and we got to the answer. Again, it's always a good idea just to convince yourself, plug this into Desmos, and make sure you get the answer you expected. The final example, and the one that people perhaps find most tricky, is one with an absolute value. The limit as x tends to 4 from the negative direction of the absolute value of x minus 4 divided by x minus 4. So we break it into two pieces below the value of 4, because that's where critical things are happening here in terms of the absolute value. Okay, so if x is greater than 4, then we know that the absolute value of x minus 4 is the same as x minus 4. And therefore, our function is just x minus 4 over x minus 4, x minus 4, which is 1. So everywhere above 4, this function has a constant value of 1. Let's just sketch it over here quickly. So here's 4, and if I'm above 4, my function has a value of 1. Okay. If I'm below 4, so for example, if I was at 3, then the absolute value of 3 minus 4 would just be 1. So that is the same as the negative of x minus 4. And so I can write f of x in this region is negative x minus 4 over x minus 4. And these guys cancel out to give me negative 1. So everywhere below 4, the function is negative 1. But we're being asked for the limit as x tends to 4 from the negative direction. And that is simply negative 1. And if you like, you can check your answer by feeding in x equals something very, very close to the value of 4 coming from the negative direction, and you'll get something very, very close to negative 1. Okay, that concludes this part 2 of limits. I think you know everything you need to know now to proceed with the next video, which will be on the derivative function. Thank you. Don't forget to like and subscribe.